Dear students, welcome to the lecture series on the topic Engineering Graphics. Today we are going to discuss about development of surfaces of solids. I am Dr. IPS Ahuja, Professor, Department of Mechanical Engineering, Punjabi University, Patiala. Now today we are going to discuss about development of truncated cone, and this development of truncated cone will be carried out by using the principles of radial line development method. So in the previous lecture we had discussed about how the development of the cone is being made. Now today we are going to see that how a truncated cone will be developed using the principles of the radial line development method. So we have been provided with a right circular cone having base 54 millimeter and the height 72 millimeter, and this cone is resting with its base on the horizontal plane and a sectional plane which is perpendicular to VP and inclined to HP at an angle of 45 degree, that is AIP. So auxiliary inclined plane, which is inclined at an angle of 45 degree. It cuts the cone bisecting the axis. So here you can see this is the axis of the cone. O is the top apex portion and O1 is the point of the axis at the center of the cone, and this is an AIP which bisects the axis of the cone, and the angle of inclination of the AIP with respect to the horizontal plane is 45 degree. Now we are required to draw the sectional top view and also show the development of the lateral surface of the truncated cone. So let us start working on the basics, that is the projections of the cone which is uncut, right? So first of all, since this cone is resting on the horizontal plane on its base, so if we look at this cone from the top, so the top view will reveal the circular portion, that is it will be drawn on the horizontal plane, and this will be drawn below the XY reference line. So the diameter of the circle is given to us. This is equal to 54 millimeter, right? So this is the diameter of the cone. So if you look at it from the top, a circle will be visible, and this circle or the cone we are going to divide into 12 equal parts so that larger number of generators are available, so that better development we should be able to obtain. So we have divided this base of the cone into 12 equal parts so that 12 generators starting from point O to all of these points, so they will be revealed over there. So the access point has been located, and then you see the 12 points which are lying on the base of the cone over there, so they are also marked onto the top view of the cone over there. Now having developed the top view, now we need to draw the front view. So this is the top view of the uncut cone, right? Now let us draw the front view of the uncut cone. So we know the access point, access height value is equal to 72 millimeter, that is the height of the cone is 72 millimeter. Now you see we have drawn the axis, marked the point 72 millimeter. This point will be point O dash and this point will be O1 dash over there. So the access point at the apex or the vertex will be called O dash corresponding to this point O, and the bottom point will be O1 dash, and then the projections of all the base points onto the vertical plane will be shown as over here, right? So just see, if you draw projector through point 1, so 1 dash will be projected on the vertical plane. Similarly, the projections of 2 and 12, they will be overlapping. Similarly, the projections through 3 and 11, they will be overlapping in the front view, so you get 3 dash and 11 dash over here. Similarly, the projections through 10 and 4, they will be overlapping at the horizontal plane over there, that is on the horizontal plane. So all the projections of the base points, they will be lying on the horizontal plane or on the XY reference line in the front view. Okay, so these are the 12 points which are available corresponding to the base on the XY reference line. Why? Because the cone happens to be resting onto the ground with its base over there, right? So we have drawn the top view of the uncut cone. We have drawn the front view of the uncut cone. Now we are given that an AIP which is inclined at an angle of 45 degree. This AIP which is inclined at an angle of 45 degree, it is going to bisect the axis of the cone. So this axis of the cone is O dash and O1 dash. This is O dash, this is O1 dash. Now one thing must be clear, that first of all we need to draw the development of the uncut cone over there. Then we will see how the cutting is done, and then the rest of the procedure will be followed. Now in order to draw the development, you see, we need to work out the true length of the slant edge. So these are 12 slant edges which are available in case of a cone. So out of those 12 slant edges or slant generators that we have in the case of a cone, we'll find that, you see, the interior ones, that is O dash, 2 dash, O dash, 12 dash, O dash, 3 dash, O dash, 11 dash, similarly O dash, 4 dash, O dash, 10 dash, O dash, 5 dash, O dash, 9 dash, and then O dash, 6 dash and O dash, 8 dash. So these 10 internal generators which are there, which are shown in the front view on the inner side, they are all the apparent lengths. Why they are the apparent lengths? Because you see in the plan, O2, O12, O3, O11, O4, O10, O5, O9, O6 and O8, they are all inclined to the XY reference line. So these 10 generators are there, 5 on the upper side, 5 on the lower side. They are all the generators which happen to be inclined to XY. So the front view is also inclined to XY and the top view is also inclined to XY. But there are two generators which are having the special characteristic, that, please check, O1 and O7. So O1 generator or the slant edge, it happens to be parallel to the XY reference line. So since O1 slant generator is parallel to XY reference line, so therefore in the front view, O dash 1 dash, this slant generator, this will be giving us the true length of this slant edge. Similarly, O7, you see O7 also happens to be parallel to the XY reference line. Therefore, O dash 7 dash will be the true length of the generator over here. So in the front view, you see, we have O dash 1 dash and O dash 7 dash. Now for the purpose of development, we have to draw an arc in the radial line development method. This will be our center point and this much radius we will be opening, and the true length of the slant edge, this will be equal to the radius of the arc which has to be drawn over here, and this distance has to be equal to the true length over here, that is O dash 7 dash, or it can be O dash 1 dash, right? So radius is O dash 7 dash and O dash 1 dash, and this is equal to true length. And true length of what? It is the true length of the slant edge basically, right? So this is the slant edge. We are not bothered about this 72. So this slant edge will be higher than the value of the 72 because this is the hypotenuse. Okay, so in this triangle, you see 72 is the height. So here we had 54, 27 is the base. So this is the altitude that this is the, you see, hypotenuse that we are getting. So altitude is the axis, 72, base is the radius, that is, this is our base which is 27. So mathematically also we can work out this hypotenuse of the triangle, O dash, O1 dash and 7 dash. But we are going to work it out using the construction method. Now whatever length has been observed over here corresponding to O dash 7 dash or O dash 1 dash, now using this slant edge, you see, with O dash as the center, please see O dash is the center. I have opened compass this much and arc will be drawn. This is a long arc that we are going to draw because we don't know where the circumference length of the base of the cone is going to end. So the circumference length will be 2 pi r, or it will be equal to pi d. So technically and for the purpose of practical manufacturing, we'll start from point 1 and then move along this particular length. Total 360-degree rotation should be there till we reach this point. So this will be 2 pi r or pi d, and whatever length comes, so this length has to be transferred over here and then divided into 12 equal parts over there, right? This is the ideal situation, or the situation required for the industrial development, or whenever we are using the AutoCAD we can follow these things. But in the usual manual drafting, you see, we are not able to measure this arc length over there between 1 to 2, 2 to 3 and 3 to 4. So what we have, instruments, we have the instruments like divider, compass or scale, and they all measure the linear distance, not the distance of the arc over there. So practically we should be drawing this particular thing theoretically, and even practically also this is the requirement or desirable length which we should have drawn corresponding to 12 sectors over here. But here the limitation of the manual drafting is going to hamper the development of this cone. That is what we are going to do. We will be measuring the chord length between the point 1 and 2, and similarly 2 and 3, and all the chord lengths, they will be equal because the sector angle is between 1 and 2 30 degree. Similarly 2 to 3 again it is 30, 3 to 4 again it is 30 degree. So we'll measure only one sector length because all sector lengths, they will be equal. But if we are going to draw it using paper and pen or pencil, then this chord length will be measured, not the arc length. Or if you want to really prepare a model, then what you can do, you calculate 2 pi r and then divide it by 12. Calculate pi d, that is the circumference of the circle, if you want to prepare an exact model. So for preparing an exact model, you can do measure this 2 pi r, calculate and divide it by 12 and make 12 arcs over there. Okay, but if we are drafting for the class, then we have to mark this distance of linear distance over here, that is the chord length will be drawn. So this sector angle will be slightly shorter than what it should be, what we are going to get over here in the class. Okay, so this is what we are going to do. So please check. Having clarified that, we are going to draw this chord length which will be slightly shorter than the arc length. So we call this method as an approximate development method. Usually, ideally, we should have drawn pi d divided by 12, then it would have been the accurate method. And it's not that it cannot be done. It can be done. But for manual drafting, we are going to choose linear distance over here. Chord length we are going to draw because we don't have any mechanism to measure. So mathematics we are not going to use over here. So we need to just demonstrate the method of development. So even though this is an approximate method, right? Now what we are going to do, as I told you, we have measured the chord length. Ideally it should be the arc length. So we have measured the chord length. So 12 arcs, you see, we are going to draw. So starting from 1, my radius of the arc is this one, O dash 1 dash or O dash 7 dash, and then 12 arcs they have been marked. The moment you mark 12 arcs, you see you have started from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and again you get back to 1. You see, you start from here, you need not end at 12. If you end at 12, you will be making one arc short or one sector short over there. You see, this is my first sector, second sector, third sector, fourth sector, fifth, sixth, seventh sector, eighth sector, ninth sector, 10th sector, 11th sector. So if I am making arcs up to point 12, so 11 sectors I am able to open, but I need to end at the same point. The starting point of the development and the end point of the development has to be the same. So having drawn 12 arcs, then what you need to do from this center, so all the radiating, you see, generators, artificial generators, they need to be drawn with 2H pencil. So just see, now I am going to join O dash with all these points of the arcs. Now this is the development of the cone which has not been cut. Okay, so the first portion we have completed, that without cutting the development has been prepared over there. Now we are going to take care of the cutting plane, see how it cuts the particular cone over here, and then we'll see how we are going to obtain the sectional top view, and then the cutting points, that are the points of intersection, will be transferred from the front view to the view of my development over here. So let us start working upon that. So I know the point. So the point of intersection of the cutting plane with the axis is bisector. So I have worked out the bisector point. You see, this is my bisector of the axis of the cone, and once I get the bisector of axis of the cone, I can draw an auxiliary inclined plane. What is an auxiliary inclined plane? It is a cutting plane which happens to be perpendicular to VP and inclined to HP. So I am going to draw an AIP inclined at an angle of 45 degree to the horizontal plane. So once you draw this cutting plane, what we find? We find that this cutting plane is cutting, or it is intersecting all the 12 generators. Whatever slant generators are there, it is going to pass through all those 12 generators over there. You see, these are all slant generators. So all these generators, they are being cut by this cutting plane. So how many points of intersection we are going to have in this case? So since there are 12 generators, so all of them, they have been cut by the cutting plane at different locations, obviously depending upon the angle of inclination. So we are going to get 12 points of intersection. Let us do the marking of all those 12 points of intersection. So here you can see, once again the same chronology we are going to follow. O dash 1 dash will be cut at point A dash, O dash B dash will be cut at point B dash, O dash C dash will be cut at the point C dash, O dash D dash will be cut by the cutting plane at the point D dash. Similarly, O dash 5 dash will be cut at the point E dash, and O dash 6 dash generator will be cut at the point F dash, and then O dash 7 dash will be cut at the point G dash. Similarly, O dash 8 dash will be cut at H dash, O dash 9 dash will be cut at I dash, O dash 10 dash will be cut at J dash, O dash 11 dash will be cut at a point which is called K dash, and O dash 12 dash will be cut at a point L dash. So all these 12 points we have marked over here, and we can see on the outermost generators only 1 point is lying, whereas on the interior 5 generators, so 2 points they are lying on every generator. So it's not that it is cutting it twice, because the you see two slant generators, they are overlapping each other. So there are 12 generators. On the outermost side 1 generator is there, whereas on the innermost side you see 5, you see double generators are there, because both ends, this end and this end, they are overlapping. 2 and 12 are overlapping, 3 11, 4 10, 5 9 and 6 8, they are overlapping. So that is why we get 12 points. Now you see, having located these points in the front view, so POIs, that is the point of intersection of the cutting plane with the 12 generators, they have been obtained. Now we need to transfer these points onto the top view. So we have to transfer these points to the top view, and this we have already demonstrated while we were discussing the topic of section of solid. So there also the section was cut by a cutting plane, and these points they had been transferred onto the top view. But since it is required that we should show the sectional top view, so we are going to transfer them in the top view. So please see, A dash is the point at which our cutting plane is going to intersect the slant generator O dash 1 dash. Now what I am going to do, I'll bring the vertical projector down. Just see, one vertical projector down I have drawn, and from A dash I have drawn a vertical projector, and it should be allowed to meet the plan view, top view of the slant generator, which is O1. So it meets it here. So this is the location of my point A in the top view. Now from the second pair of generator, you see here the pair of generator I call because two generators, that is O dash 2 dash and O dash 12 dash, they are overlapping. So on O dash 2 dash B dash will lie and O dash 12 dash L dash will lie. So from the common POI point of intersection for this dual generator, I am going to bring the projector, vertical projector down. So wherever this vertical projector meets O2, point B will be located. Wherever this vertical projector intersects with O12, that is the top view of the generator, slant generator O12. So I get the point L over here. So A is located, B is located, L is located. Now next one, C and K. Now you see C and K is again dual generator because two generators, they are overlapping. That is O dash 3 dash and O dash 11 dash. So from this dual intersection point, you see C dash and K dash in the front view. Again I have dropped a perpendicular down, and wherever this vertical projector it intersects with O3, that is the top view of the slant generator O3, I get the point C. And then wherever it intersects O11, I get the point K over here. So this is C, this is K. Now let me work out again another set of, you see, generators which are overlapping, that is O dash 4 dash and O dash 10 dash. But there is a, you see, there is a catch over here. If you bring these 2 points D dash and J dash, I bring a vertical projector down, but no point of intersection I am able to locate. Why? Because I am looking at the perpendicular location corresponding to the 2 points D and J. That is, you see, if D point is here, J is here, I am looking from this side. D lies here, J lies here. So I am looking from this side. So this, I am not able to get a intersection point if I am bringing it down. So same thing we had discussed while we were discussing the projections of solid as well as the section of solid. So then what we have to do, if we cannot see through this, because these 2 points, they were overlapping and they were overlapping on the axis. So what we have to do, rather than looking from this side, we have to go 90 degree and we have to look from this side. The moment we start looking from this side, these 2 points will be visible to us on the outermost boundary over there. Whereas from this side, even though they were lying on the outermost boundary, but they were coinciding with the axis point. So once I bring those points down, you see D dash and J dash, if I bring them down, no point of intersection is obtained. So what I am going to do, I will just rotate this. You see, there is a definite relationship between the height. You see, definite relationship exists between the height and the radius of the cutting portion over there. Let us say it was not intersecting over here, it was intersecting over here. So larger the height, lesser will be the radius. Still larger the height, radius will be still lesser. Height is reducing, radius is increasing. If the height is still reducing, my radius is still increasing. So here you see, I know the height, but radius I am not able to see because I am looking from the same side. So these 2 points and the axis, they are coinciding with each other. So what I'll do, I'll move 90 degree. So by moving 90 degree, now these 2 points, they will be visible to me. So what I am going to do, I am going to take care of this relationship of height and radius. So this is my height at which my cutting plane is going to intersect with the axis. Now corresponding to this height, you see, I am going to move 90 degree. Moving 90 degree means I am going to move from this point. I'll draw a horizontal line which will be parallel to this XY line. I am going to draw a horizontal line. Just see, I have drawn a horizontal line which will be parallel to this XY reference line, and by moving to this 90 degree position, I have transferred this height at projection point or the generation point O dash 1 dash. So I have obtained a point on O dash 1 dash. Now from here, what I am going to do, I'll bring a projector down. Just see, I'll bring a projector down. The moment I bring a projector down, up to which point I need to bring it down? I need to bring it down because it was, this point was lying on O dash 1 dash. Now I have to bring this projection point to the plan projection. So this is my point. That is on O1 I need to bring this point. The moment I obtain this point, so I have transferred this radius. What I have done, I have transferred this radius over here. The moment I transfer this radius, I'll keep the needle of my compass here, open compass this much. Now open compass this much and transfer the radius on either side, so that if I'm looking from this side, these 2 points, they are available to me, this radius and this radius. So according to height, radius will vary. Had the height been less, radius would have been more. Had the height been more, radius would have been less over there. Because if you cut it parallel to the base, so the radius will be same all around over there. So that's what we mean. If we are looking from this side, we are not able to check the diameter on this side because we were looking parallel to the axis over there. Here we are getting perpendicular, so we can easily see through the radius over here. So you see, from corresponding to this height, I have evaluated the radius and then transfer the radius to O1 and then open compass this much, take radius on the upper side and transfer radius on the lower side. So these 2 points, they are also located. What are those points? On O4, D will be located, and on O10, the point J will be located. So J is located here, D is located here. Next points, they are simple. Again, another pair of points of intersections are there. That is E dash and I dash. Where does these 2 points lie? E dash lies on O dash 5 dash and I dash lies on O dash 9 dash. Now from here I am going to draw a vertical perpendicular projector. You see, from E dash and I dash I have drawn a vertical perpendicular projector. So wherever this projector is coming from this dual point of intersection, so wherever it intersects O5, point E is located. Wherever it intersects O9, point I is located over here. And next pair is, that is F dash and H dash. So F dash and H dash point lies on the pair of projectors O dash 6 dash and O dash 8 dash. Again there is a pair because these 2 projections, they are overlapping, right? So from this pair of POIs in the front view, that is F dash and H dash, this is the point. So from this point I'll again draw another vertical projector. So this dual POI projector, vertical projector I draw, and wherever this vertical projector it intersects O6, point F will be located. Wherever this vertical projector will intersect O8, my point H will be located. And finally the last point G. So G lies on the true length, that is O dash 7 dash. You bring a vertical projector to intersect top view of O7. So this is the point G which will be located. So all the 12 points, they have been located. Just see, I have joined them, and this will be a shortened ellipse. This will be the sectioned top view which is going to show me the apparent shape of this cut section, which is going to show me the apparent shape of this cut section over there. So we have been able to draw, you see all these points A, B, C, D, E, F, G, H, I, J, K, L over here. So all these 12 points, they have been mentioned and they have been plotted in the top view. So please check, all POIs, they have been plotted in the front view. All POIs, they have been appropriately plotted in the top view. So the first portion is completed. Sectioning we will do at the end, right? So having evaluated all POIs in the front view and all POIs in the top view, now the next thing is we have to transfer, please check, we have to transfer all these 12 POIs in the development view. This is very interesting. We have to transfer all these POIs. We have 12 POIs available with us. So all these 12 POIs, we are going to transfer one by one. But one thing we need to understand, what all the POIs, when they are to be transferred over here, the distance of every POI from O dash onto the slant generator cutting point edge over here. So we cannot draw those POIs which are lying on the apparent line, because we have already discussed only O dash 1 dash is true length and only O dash 7 dash is true length. So only two, you see, slant generators are there which happen to be true length, whereas the interior pair of, you see, 5 generators are there, that is 10 generators are there which are lying inside this cone. So all these 10 generators which are there, they are apparent lengths in the front view. So I cannot afford to draw apparent length of this onto the corresponding points over here. So what has to be done, please pay attention, it is very important and very interesting as well. You see, we'll be making use of principles of rotation of line to work out the true length of the projectors, which are all these projector points, that is corresponding to 10 POIs which are lying in the interior 5 pairs of generator. So number 1, OA dash, this is true length, please check, OA dash, this is true length. So I can transfer point A straight away here, I can transfer point A straight away here. So I'll draw one arc, you see, and wherever it intersects O1, I will get the location of point A. Over here also, wherever it is intersecting, I am getting the location of point A. Similarly for G. So these 2 points are the simplest. For G, once again, I'll measure this radius, I'll have my needle of the compass here, that is my center of rotation will be here at O dash, and then I'll open compass up to G dash, and again draw an arc. So wherever it intersects O7, I don't have any problem in marking this point as G. So these 2 points are crystal clear. Then what about the remaining 10 points over there? So let us start working it out. So you see, I have drawn the first arc starting from A. Please check, I have drawn the first arc starting from A, and as I have just told you, O dash, A dash happens to be true length. So since this is true length, so all these arcs should be true lengths only. So no apparent length arcs should be drawn over here. So O dash, A dash, it is a true length. I'll mark this point as capital A. I'll mark this point as capital A because I am starting from 1, I am ending at 1. So A point will be available at 2 points. So please check, A point will be available here, A point will be available here. Now I have marked A points twice. Now I have to mark arcs corresponding to B dash, L dash, C dash, K dash, D dash, J dash, E dash, I dash, F dash, H dash. So these are the intermediate 5 pairs of POIs over there. But the problem which I am facing, that you see, this is the arc length which I can easily measure. O dash, B dash and O dash, L dash is the arc I can very easily measure, and I could have drawn it straight away over here, but I can't do it. Reason, this is an apparent length. I know from the rotation of line method that whenever you draw 2 locus lines, one at the origin point and second at the end of the apparent length, then the true length will be lying on the same plane over there. Between these 2 locus lines, my true length will be lying. So this principle I am going to use. So what I have to do, please see, I draw a locus line, I imagine I have drawn it, another locus line I am going to draw through B. Please check this out, I have drawn a locus line through B. So this is my apparent length, that is O dash, B dash, this is my apparent length, but this is the true length. Please see, O dash, this point. So this point which is obtained, that is O dash, I call this true length as B1 dash and L1 dash. So please check, so true length and the apparent length, because I have not marked the points over here because the space would have become very, you see, crunchy over here. So interference would have been there. So I am going to mark either this point or this point, because both these points, they are the same, because this is also true length, this is also true length. So what I am going to do, please check, corresponding to points B and L, the arc will not be drawn according to this distance. So what I have to do, I have drawn a horizontal line. So if this is the apparent length, so this length, you see, O dash, this point, B1 dash and O dash L1 dash. So this distance and this distance, they are the same. So I can say O dash B1 dash and O dash L1 dash. So this is my true length. So what I have to do, rather than measuring this arc, so I have to now measure the arc which will be equal to horizontal line you project from apparent length onto true length. So either you can do it here or you can transfer it here. So I will be measuring this length rather than measuring this length over here. So this length, there will be hardly marginal difference, half a millimeter, 1 millimeter, or maximum 1.5 millimeter difference will be there. But whatever may be the difference, I cannot draw the apparent length. So please, again I repeat, O dash B dash and O dash L dash lengths cannot be drawn. So what has to be done? From the apparent length point, draw the horizontal line, locus line up to the true length, either on this side, here again the true length is available, so, or on the other side. Now I will be measuring this distance, which will be half a millimeter to 1 millimeter higher than this distance of O dash, L dash and O dash, B dash over there. So I am going to draw an arc corresponding to this length, O dash B1 dash or O dash L1 dash. Now, so what we have done over here, we have marked the apparent length onto the true length. So we have transferred this apparent length onto the true length, that is, we have shifted it onto the true length O dash 1 dash or O dash 7 dash over here. So this new distance becomes, that is, O dash B1 dash and O dash L1 dash. So this is the true length of the, you see, points of intersection which are going to lie on the true length of the line, which happens to be O dash 7 dash or O dash 1 dash. So either way, you see, you can draw a horizontal line over here, and this apparent length can be transferred on this side onto A dash 1 dash, or it can be transferred onto O dash 7 dash, which is again the true length. So with this distance, that is O dash B1 dash and O dash L1 dash, which appears on the true length, so corresponding to this distance, you see, we have marked the arc in order to work out the locations of the points B1 dash and L1 dash onto the development surface over here. So we need to ignore this apparent length distance, that is O dash B dash and O dash L dash, and we need to now consider the new true length distance which is corresponding to B dash L dash. So this point happens to be B1 dash and L1 dash, and now you see, we are going to locate the generator, slant generator O2 and O12 onto the developed surface over there. So wherever this new arc which has been, you see, drawn corresponding to the new radius, which happens to be radius corresponding to the true length of the points of intersection. So these points will be B1 and L1. So L1 point will be lying on O12 and B1 point will be lying on O2 over here, right? So we don't have OB and OL any longer. So since we have marked the true length radius over here, so name of these 2 points will be B1 and L1. So B1 is located on O2 and L1 is located on O12. Similarly, the next pair of, you see, points of intersection, they happen to be C dash and K dash, which are lying once again on the apparent length of the generator, that is O dash 3 dash and O dash 11 dash over here. So once again, we cannot draw arc corresponding to this apparent length radius, that is O dash C dash and O dash K dash. So what we need to do, once again, we'll be drawing a horizontal line, a locus line will be drawn, so that these 2 points, they can be transferred onto the true length either on this side or on this side. So on the either side, now the points which will be obtained on the true length, they will be called C1 dash and K1 dash, because true lengths, they always have the suffix 1 or 2. So these, you see, points which were corresponding to the apparent length C dash K dash, so once you transfer them onto the true length, Now we are able to obtain this new radius, and this new radius will be O dash C1 dash or O dash K1 dash. So again over here also you get the same radius, O dash C1 dash and O dash K1 dash. So we need to once again ignore this apparent line radius of O dash C dash and O dash K dash, and now we have to take this true length distance of the POIs C and K, and this new radius will be O dash C1 dash and O dash K1 dash over here. So with this as radius, that is O dash C1 dash and O dash K1 dash as radius, you see we have drawn another arc, and we'll find out the two, you see, slant generators O3 and O11. So wherever this new arc, it is going to intersect with the two generators O3 and O11, I am going to get the location of the 2 points of intersection, that is C1 and K1. And again I repeat, it is not OC and OK, it is OC1 and OK1, because I have marked the arc corresponding to the radius which was for the true length, not for the apparent length. Now the next point, you see, pair of points of intersection, they happen to be O dash, D dash and O dash, J dash. That is D dash and J dash, they are the points of intersection of the cutting plane with the slant generators O dash 4 dash and O dash 10 dash respectively. But again, this is the apparent length generator that we are able to visualize or see in the front view. So once again, we cannot take this radius over here. So we have to transfer these points onto the true length. So since true length is available on either side, so I can transfer it on this side or on this side. So the 2 points which are obtained on either side of the, you see, apparent length, that is on the true length. So the name of these points will be D1 dash and J1 dash. And now if I measure this radius O dash D1 dash and O dash J1 dash, so this true length radius will be greater than the apparent length radius of O dash D dash and O dash J dash. Now I have obtained this new radius, which is the true length of the points corresponding to the radius, that is O dash D1 dash and O dash J1 dash. Again another arc I am going to draw, and now I need to find out the point of intersection of this arc with two slant generators, that is O4 and O9, O10 over here. This is O10 and here you have O4. So wherever O4 and O9, they are being intersected by this arc, so I get the locations of the point D1 and J1. So again these points, they are not D and J because I haven't marked the distances corresponding to the apparent length. Since I have marked distances corresponding to the true length over here, so the names of these points will be D1 and J1, and this radius will be more than the apparent length radius over here. Then the next, you see, pair of points of intersection, they happen to be E dash and I dash over here. So E dash is the point of intersection of the cutting plane on the slant generator O dash 5 dash, and I dash, it is the point of intersection of the cutting plane with the slant generator O dash 9 dash. Now once again, this radius, that is O dash, E dash and O dash 9 dash, this is lying on the apparent length, and I cannot take the apparent length because I have to develop the true length distances in the development. So what I will be doing, again from E and I am again going to draw a horizontal line wherever this horizontal line intersects with the true length of the slant edge. So if I transfer these two distances corresponding to E and I onto true length, so the new points I obtain will be E1 dash and I1 dash, and this true length radius, you see this one, this true length radius of OE1 dash and OI1 dash will be greater than the apparent length radius of OE dash and OI dash. So now once I have found out the true length radius corresponding to the POIs E and I, now another arc I am going to draw, and once I draw this arc, I need to find out the points of intersection of this new arc with my slant generators O5 and O9 over here. This is O9 and this is O5. So wherever this arc intersects these two, you see, slant generators, my new 2 points, that is E1 and I1, will be obtained over here. So the two new points of intersection, they have been located in the development surface over there, right? Next I have got, you see, another two pairs of points of intersection, F and H. So F dash and H dash, these 2 points lie on the slant generators O dash 6 dash and O dash 8 dash, which is again lying on the apparent length. So I cannot take this distance, that is O dash F dash and O dash H dash. So again I will be drawing a horizontal line so that this apparent length distance can be transferred either on O dash 7 dash or on the O dash 1 dash. So once I obtain the true length corresponding to these points of intersection, that is F and H, so this point corresponds to the radius for the POIs F1 dash and H1 dash. So another arc I have drawn, and once I draw this arc, now you see I need to work out the points of intersection of this arc with O6 and O8. O6 and O8. So wherever it intersects O6, I get the point F1, and wherever it intersects the O8 on the surface slant edge, I get the point H1 over here. So please check all these points, they are having suffix 1 because we have worked out the true lengths corresponding to the apparent radii which were appearing because the POI was obtained on the slant edges which were shown to be reduced length or apparent lengths over there. And finally my point G, because G point and 1 point, they lie on the true length, so no A1 or G1 will be there. Initially we had drawn only A point, now we will be drawing radius corresponding to simply G. So whatever you see apparent radius is there, true radius is also the same. Why? Because G dash point lies on the true length O dash 7 dash. So this apparent radius, that is whatever is visible, is the true radius. So now I just draw the horizontal line and then draw the arc corresponding to radius G dash. No G1 dash is there. So please see in this figure, point G is located on the intersection of this last curve with the slant generator O7 over here. Now in this entire figure, only A and G points you see which I have highlighted with blue. So these are showing that these points have been transferred from the true length. So no special true length generation procedure was followed. Whereas for the rest of the, you see, 10 points of intersection which were lying on the intermediate slant generators over there. So we have to work out the true length for all these points of intersection. So having obtained all these points of intersection onto the developed surface, now I will be joining all these points freehand. You see, I have been joining this. So whatever figure is left out, that I have darkened. So this portion I have darkened. So this portion I have darkened. So I have been able to obtain the surface of development corresponding to this truncated cone over here. So if I just carry out the rolling of this, I will be able to obtain the perfect cone which is being cut by a cutting plane at an angle of 45 degree, right? So this way, and similarly, now I will be completing the section top view as well. So the section top view was completed, so only the shading portion was left. So the hatching has been done at an angle of 45 degree to the XY reference line. So this completes our discussion regarding how to obtain the section top view of the truncated cone and how do we make the development of the truncated cone which has been cut by an AIP which is inclined at an angle of 45 degree to the horizontal plane, and this cutting plane is bisecting the axis of the cone, right? So these two conditions, they have been met over here, right? So this was all about the discussion regarding the development of the truncated cone. So we will be continuing with the further presentation on few more cases regarding development of surfaces in these next lectures. So thank you very much. Thanks a lot. Thank you.